Fireside chat, which, like many things at this conference, is virtual. So, and I suspect there's not a fireside, even a virtual fireside. The presentation is by Chris Lattner, who co-founded the LLVM Compiler Infrastructure project, the Clang compiler, the Swift programming language, the MLIR compiler infrastructure, the Circuit project, and he's also contributed to other projects at Apple, Tesla, and Google. He now leads engineering and product teams at Sci5. He is going to be interviewed by Hal Finkel, who's a computer science program manager in the US Department of Energy Office of Science's Advanced Scientific Computing Research Program. Hal serves on the LLVM Foundation's board of directors, and he represents DOE on the C++ Standards Committee and serves as vice chair of the committee. As a compiler researcher myself, I'm really excited to hear from both of them in this next session.
Okay, great. Well, thank you, Chris, for agreeing to do this. And I'd like to thank Vivek Sarkar and the organizers for inviting me to have this fireside chat with Chris and be able to share that with the entire community, sans the actual fireside. And
we did the best we can in the virtual world.
Yeah, exactly. So we'll make do. And I'd like to start out by saying that there is a Q&A set up for this chat on Hub, and I have some questions, and I'll try and keep an eye on the Q&A and integrate things into the conversation as I can. With that, let me just I'll start out by saying we're here because of LLVM. LLVM is now an inescapable part of the HPC programming environment, just about regardless of what platform you're on. And so I'll start by asking Chris, can you provide, perhaps for the benefit of audience members who are less familiar with LLVM, some brief overview of what LLVM is, and then we'll get on to some history and other exciting things.
Sure. So to me, one of the most the biggest part of what LLVM is it's a big community of people. They're all collaborating together, that have common interests, they're all working to push technology forward. And so if you go back to its roots, LLVM is about taking compiler technology, and instead of building one monolithic batch compiler that does one thing, maybe with a pluggable parser or pluggable code generator, about taking all the technology problems that exist within compilers and decomposing them down into their component pieces, which can then be reused. And originally, this was a software engineering goal of saying, okay, well, let's make it so it's easier to test and easier to swap out components and things like this. But one of the contributions that enabled is it allowed the community to scale, because compilers, like many of the large-scale software systems that you build, end up being so complicated they don't really fit in any one person's head, not even mine. And so by being modular, it's allowed communities of experts to descend on the register allocator or the x86 or the PowerPC code generator or whatever it is, and become specialists in their area, making the system better and then scaling it up. And so today, LLVM has grown to the point where it encompasses a wide range of compiler and toolchain and high-performance computing and runtime kind of technologies together, all unified by a common value system of building high-quality, well-engineered code that is modular, that works well together, and that is free to use for all kinds of different purposes.
Okay, great. And so now that having been said, I mean, you're the person behind LLVM. So let's you started it all, so to speak, and let's give the audience a little bit of a better understanding about who you are as a person. So
Sure.
From before you started in college, say, can you say something about a couple of sort of life-defining moments? Like how did you get to that point in your life and sort of decide to be in that place?
Yeah, so for me, I went to a little high school out in the middle of nowhere and in kind of a rural part of the Portland, Oregon area, and didn't really have other people that were interested in technology growing up with me. I went to the University of Portland in downtown Portland, which is a private college, and I entered into the ROTC, the Air Force ROTC program, so that I could get my way paid through college and then go into the Air Force. And for me and my parents at the time, that was a really important deal. We didn't have a lot of money, and so it was a good way to get a 4-year expensive private college paid for. This all went really well until I had this really amazing professor who happened to like compilers and computer science stuff. And he was talking about, yeah, maybe you should go to grad school someday. And I said, well, what do you mean grad school? And why would I want to do that? And he says, well, this is actually a great way to explore the next level of things that are going on, differentiate yourself from other folks that are graduating and things like this. And I started to realize that going to the Air Force was not for me. And so I decided as a sophomore, without really knowing much of what I was doing, that, yeah, maybe I should not do this. And so I pulled myself out of this program, only to find myself with a lot of interesting life-defining consequences where, first of all, I had government debt collectors coming to try to break my kneecaps and get paid back for all the tuition they had paid. And my parents almost sort of disowned me, and we since fixed that. But what this did was this thrust me very early into the world of going and creating software to make money so that you could actually pay for school and get out of debt and all that kind of stuff. And for me, I think this was a big moment because it kind of forced me out into the real world. And instead of being taken care of by other people, it was kind of figure it out and, work your way out of a box that you find yourself in. And so it all worked itself out and it was good. And so I was happy to go on to the University of Illinois and be able to do LLVM and other things like that. And so I love building things and working on hard technology problems.
Okay, great. Well, let's kind of pick it up there then. And so, LLVM ended up being your master's thesis project, as I recall. And so can you say a little bit about how that happened? Like, what were you hoping to demonstrate, and how did you decide to start that project?
Yeah, so I was hired into Vikram Advai's research group at the University of Illinois. I was one of his first students that he hired when he joined the faculty there. And so we were all really interested in this evolution of computing. And at the time, this was back in 2000 kind of time frame, Java was taking over the world. It was really exciting, and nobody knew the boundaries of Java. Some of us had some concerns about certain workloads that maybe wouldn't fit super well with it. But the compilation story was still quite early, and the just-in-time compilers were just coming in. And Vikram and I had this idea that, hey, well, if we took this just-in-time compiled technology platform, but did more ahead-of-time compilation, then we could get better trade-offs in terms of whole program optimization, analysis, be able to build analysis tools, things like this, and get better performance. And so a lot of the name LLVM, low-level virtual machine, comes from the idea of taking the Java virtual machine and building something that is underneath it and building a platform that you could then do whole program optimization for this and go. Now, this whole thing, that whole theory in the name is not a great name in historical terms, because I think that lasted about 6 months. And about 6 months in, after building a whole bunch of infrastructure and learning all this compiler stuff, which I was just eating up and I just loved learning by doing, we actually ended up saying, well, how about we build a code generator and how about we go integrate with GCC? And so very early on, it started as a Java thing, but ended up being a C and statically compiled tooling language target as the initial focus. And so a lot of that early genesis kind of got derailed, but it became a very useful platform for research and for applications in a large number of different domains. And so it's been a lot of fun to see that. And eventually Azul and others kind of brought it back into the Java world. But it really came from, I just was having a lot of fun reading the papers, implementing the algorithms, trying to learn and understand how things worked end to end. There's a lot of value in particularly in a research setting, of just implementing the whole thing yourself, because you get a much more visceral understanding of the problem space and the trade-offs than you do even reading good, high-quality research papers. And so had a lot of fun with that. At the same time, then the research group was scaling, and so we had the ability to take on newer and bigger challenges, and just kind of eventually Vikram decided that it would be a good idea to try teaching one of his compiler optimization classes using LLVM. And so let me tell you, having a whole bunch of students trying to use your work is a very eye-opening experience, and drove the focus on quality that I think really helped out. And so we eventually open sourced it, and as we open sourced it, again, the community broadened out and got more people involved. And as you get more and more different kinds of people involved, we've worked very hard to kind of foster this spirit of collaboration and help build out the community.
So I'm sure we have a lot of graduate students or people who are going to be in graduate school soon in the audience. So I should ask, do you have lessons that you learned? I mean, perhaps aside from the idea of really doing things yourself to kind of gain that end-to-end experience that you'd like to share with others who are in graduate school.
Yeah, so I wouldn't say I'm a long ways out of my grad school at this point, so I don't know how current it is. But my philosophy on this is that there isn't one true path, right? And so my experience in grad school is a little bit different than some, because I was way more interested in building the thing than writing the paper. And I will share that this caused a bit of friction with Vikram and myself, where he was very interested in getting the publications and and building that track record. And I valued that, and I enjoyed working with the community and going to the conferences and things like this. But I was just having even more fun building things. And so for me, the graduate student journey was a lot of learning about how to work and how to communicate and how to give good technical presentations and things like this. And also at some point I figured out, okay, well, these are the hoops I need to jump through to get the degree. And so once I could understand what the hoops were, then I understood how to kind of eventually work my way through the system. But for others, I mean, if you're trying to push the state of the art of science, then there can be completely different angles on that, right? Where you're looking at what is the highest leverage technology and software and other systems that you can build on top of. And how do you recognize and look deeper into the future, into the unmet need of technology, right? And so there's many different kinds of paths, I think. And I think that each person, it really depends on what your interests are. And as with anything in life, I think the key thing to do is discover and find out what you're really passionate about, what you enjoy doing. So it feels like it's fun and you're learning and growing and doing cool stuff. And that way it feels a lot less like work. And if it feels like it's fun, then you'll just be much more self-motivated to do things.
Great. So after you graduated, I suppose it's at least well known within the compiler community that you ended up at Apple and convinced Apple somehow to invest significantly in LLVM and Clang and this project. So can you tell us anything about how that happened? How did you end up transitioning this from the academic space, transitioning LLVM from the academic space into the commercial space so successfully?
Yeah. So I graduated in 2005, and so LLVM was 4 or 5 years old at that point. It was still very much an advanced research project. Okay. And so it was not fully end-to-end for all the features. The quality of the generated code wasn't perfect, but it was promising. And it was making very good progress. And one of the things that I was doing and we were doing is reporting every 6 months or 12 months we'd do a release. And the changelog would have huge progress. And so 2 things came together that worked out really well with Apple is that an engineer at Apple found LLVM and he was having a lot of fun. And I was working with him over mailing lists. And so he, a great early initial contact. But then he said to one of the VPs at Apple, hey, this LLVM thing's really cool. And at the time was right. Apple had been investing a lot in GCC. And I don't know if it was the GCC technology or the GCC team at Apple at the time, but management was very frustrated with lack of progress from the GCC team. And so I got to talk with this VP who really thought compilers were interesting, and he decided to give me a chance. Right? And so he hired me and said, yeah, you can work on this LLVM thing. Show that it wasn't a bad idea. And I found out later, he kind of motivated me later, and he says, yeah, well, you can have a year or so to work on this, and worst case, you're a smart guy, we can make you work on GCC. And so I was pretty motivated to prove that this was worthwhile. And there's a whole bunch of really challenging and interesting and motivating steps along that way. So for example, I joined, and there was a team of a dozen folks that were working on GCC. And these were industry veterans that had been working on this stuff for a long time. One of them I distinctly remember was my second week on the job or something. So I'm like fresh out of school. I don't know anything. I still don't really know much of anything. But a couple of weeks in, this grumpy, experienced compiler engineer is like, "What are you doing? Why are you here?" I'm like, "Well, I think it's really exciting to go work on this stuff, and I have all these ideas." He's like, "You don't understand. GCC has been around for 20 years. It's had hundreds of people working on it. Nothing's ever going to replace GCC. You're wasting your time." And I said, "Well, I don't know. I'm having fun. I'm not worried about the big picture. I'm just going to do my thing and have and learn and build and show more progress, right?" And what ended up happening is that at some point in time, management's like, "Okay, well, you're working on this stuff and you're making good progress. How is it useful?" And we went around and started talking to a bunch of the product teams within Apple. And the first, and the VP was like, "Oh, we're going to replace GCC and make our spec scores really awesome and things like this." And I got talking to people, and I found out that there was a huge need for just-in-time compilers in the graphics space. And so the OpenGL team was struggling because Apple's coming out with 64-bit Macs and, moving from PowerPC to Intel and a bunch of these things. They're using hand-rolled just-in-time compilers. And so we were able to use LLVM to solve a bunch of their, enable some new hardware kind of problems. And so not something that GCC was ever designed to do. It was servicing a market that was unmet. And as part of this, it was the ability to say, okay, well, this thing is now shipping in this tiny little corner of the 10.4 Tiger release, and so it showed some value and it justified a little bit of investment. And so I got another person to work with, and then we went from that to another little thing and to another little thing, and one little step at a time and one win at a time. It kind of gained momentum, and eventually it started replacing parts of GCC. Other things along the way is that the GPU team was trying to make a shading language for general purpose GPU compute, which turned into what we know now as OpenCL. And so that became the first user of Clang and was the reason I had to implement code generation in Clang and things like this. And so there's just many interesting problems that came up across the span of years. And it was always, okay, what do we have? Make sure that we're evolving and iterating and expanding it in a well-considered and well-designed way, but then building onto the next and the next and the next and the next step, and just kind of taking things one step at a time.
Okay. And I suppose to kind of pull on that a little bit, obviously, LLVM has grown significantly since then. There has been a lot of community growth and a lot of contributions. So it's also true, of course, that a lot of these contributors to LLVM are from companies and organizations that are competing with each other. And I was wondering if you can share any challenges or lessons that you learned in convincing or helping to grow this community and coalesce it, even though it's composed of organizations that in many cases compete with each other.
Yeah, absolutely. That's been one of the biggest challenges that, in one of the ways I think that LLVM is not unique, but very, very distinguished in that way. You look at the LLVM community and you have Intel and AMD and Apple and Google and Sony and all these folks that are all collaborating. And to me, one of the ways that we did this is that we made it all very driven by technical excellence and driven by a shared value system and driven by a shared understanding of what success looks like. And so one of the things we did is that I think we as a community always worked engineer to engineer to solve problems. And so often what you'll have people, so for example, me when I was at Apple or whatever affiliation, I'd have my LLVM hat on when working with the community, but then I'd have my Apple hat on where I'm solving the internal problem for the hardware that has not shipped, right? And so what we decided was that intra-corporate hat that many of us wore would not be part of the LLVM community. And so it was not about bringing, I need to get this patch in now to hit a release. It's about, well, what is the right thing, and setting and making sure that value system was always there. And because we had a shared understanding and shared way to evaluate that, both we were able to work on very hard technical problems where we had shared interests, but also we were able to scale the community. because as new people joined the community self-reinforced a bit. We had to write a lot of things down, of course, and but that allowed the community to grow and scale. And I'm very proud of the fact that we do have people that are, harsh industrial enemies that are fighting with each other on the business landscape, but that can still work on and agree about, the best way to model some kernel in GPU land or whatever it is. And I think that is extremely powerful. Building a community is really hard. And so one of the things we've had to do over the course of years is not often, but we have had to eject people out of the community. And it's when people have decided that they do not align with the value system, they're not willing to collaborate with people, or they're just not aligned with where the community needs to go. We have had a couple of people need to leave, and that is super difficult because some of them are prolific contributors, and there's a real pain. But maintaining that community cohesion, maintaining that value system is so important. You have to stay true to your principles.
So let's see. I suppose before we move on from LLVM, I'm just taking a look at the questions that the audience has asked, and one of the most significant questions here is, what do you think are the biggest challenges or issues facing LLVM going forward?
Oh, that's a great question. So I am the biggest critic of LLVM because I know all the problems. LLVM, it's funny to note, it's over 20 years old now. Right. And so LLVM is definitely a good thing, but it is not a perfect thing by any stretch of the imagination. And so I'm really happy that we've been able to continually upgrade and iterate and improve on LLVM over the course of years. But it's to the point now where certain changes are architectural and it's very difficult to make those. And so one example of this is that the LLVM compiler itself is not internally multi-threaded. And I don't know about you, but I think that multi-core is no longer the future, right? And so there's also certain design decisions, which I'm not going to go into in detail, that are regretted, things like this. Now, many of those, only a nerd like me really cares about, and so they are not the strategic kind of a problem that faces the community, but others really are. And so one of the things that LLVM has never been super great at is loop transformations, HPC-style transformations, auto-parallelization, OpenMP support. It works and it's very useful, but it could be a lot better and things like this. And so those all go back to design decisions in LLVM, where the LLVM view of the world is really kind of like a C with vectors kind of world. And so C with vectors, you don't have parallel for loops, you don't have fork join like constructs and things like this. And so that original design premise really is holding back certain kinds of evolution. Now, the LLVM project overall includes new projects, including MLIR and other projects like that are breaking down these barriers and solving some of these problems. But typically when people ask about LLVM, they're thinking about Clang and the standard, the C++ pipeline, and it hasn't quite adopted all the new technology in the space.
Yeah, our audience definitely is pushing us to be controversial here. One of the questions is, given that LLVM is taking over large parts of the compiler space, and despite being modular, it's certainly large, and some parts of it are slow, and so on. Would you recommend starting over again?
Yes, I did. This is what MLIR is, right? All kidding aside, LLVM is slow when you're using it in ways it wasn't really designed to be used. So, for example, the Rust community is well known for pushing on the boundaries of LLVM performance because their compilation model instantiates tons and tons and tons and tons of stuff, and then specializes and specializes and specializes it all away, kind of, right? And so this puts a huge amount of pressure and weight on the compiler that a C, for example, or simpler lower level languages don't have. Now that leads to amazing things in the Rust community, but like it's actually asking the compiler to do all this work that has to be done, and it's just kind of implicit in its programming model. Now, starting all over from scratch, you have to decide what problems you want to fix, right? And so the problems that I'm interested in fixing with LLVM come down to it doesn't model higher level abstractions like loops very well, things like this. I think that the constant time performance of any individual pass is generally okay. I think that the other challenge I see with LLVM is that it's a complicated set of technology, and it's therefore a difficult tool to wield unless you know all the different pieces. And so sometimes, again, depending on exactly what the complaint is, people are running lots of passes that shouldn't be run or things like this. So yeah, but I guess I'm not religiously attached to LLVM being the perfect answer. And again, I see all the problems with it. It's got a bunch of very useful technology, and one of the things I'm very much a proponent of is continually pushing forward. And so I think the LLVM community has many different constituents, and so sometimes it's hard to do that, but I am seeing some progress in a bunch of exciting areas.
All right, I'll just throw in this other question from the audience. What is your take, if you have one, on the efforts to add Fortran within the LLVM community?
I love it. I love two things. One is that it's happening, but second of all, that there's one project and people are seeming to collaborate on it with the F18 project. And so before, there was a period of time where it looked like there might be 3 or 4 different things going on in the space. And the Fortran community is really important, but it's also, the Fortran compiler community is pretty small. And so dividing the effort would have, just been a waste of people's bandwidth and things like this. And so I love to see this. I also love to see that they're looking at building a way better Fortran compiler than the existing ones, not just something that checks the boxes on features and functionality. And I think that's one of the things that when we did Clang back in the day, we weren't just looking at building a C or C++ parser. We're looking to be able to enable tooling and a bunch of ecosystem features around the language that went beyond just implementing a parser for the language that then you could generate code for. And so I'm very excited to see that.
Yeah, that sounds great. So it's final thesis, MLIR. Good. So after you, LLVM was a large success. You also led development of the Swift programming language at Apple. And I was wondering if you can say a little bit about that. What really motivated that development, and what were viewed as the largest risks when the project started, and were you right about that?
Okay, so again, this is you have to separate out the me being a nerd versus the strategic imperative of doing a new language, right? And so the origin of the Swift language was we got done with Apple's WWDC conference in 2010. We just launched the Clang C++ compiler, shipped it out in the first beta to all the developers in the Apple ecosystem. It could bootstrap, it could build Boost, it was becoming incredible, but it certainly had a long ways to go, right? And to me, so I've written millions of lines of C++ code, literally, built at least a significant chunk of the Clang compiler, definitely not the whole thing. And so going through that experience, you can't help but think that there could be a better language than C++, right? C++ is amazing, it's powerful, it's great, but it's not a beautiful thing, okay? And so coming out of that, I just started nights and weekends saying, okay, well, here's what I think should be in a programming language. It should have zero-cost abstractions. It should be easy to learn. And you should get the defaults right in C++. You should take advantage of all these innovations that have happened in programming languages that are academic, and we should be able to pull these together and build something that is good and scalable and wants to prove these things. And it was just kind of a research project for me. And I did it nights and weekends on spare time. Worked on it for a year and a half, something like that, before I really started talking to people at Apple about it, and got to the point where it kind of, I had the ideas and the principles in my head of what I thought would make sense. And so then I broached it with management and said, hey, how about we have a new language to replace Objective-C? Wouldn't that be exciting and great? And think about how wonderful everybody would find that. And the reaction was, what are you talking about? I'm like, what? What do you mean? What are you talking about? Like, well, Objective-C is what made the iPhone successful. Like Objective-C, I mean, it has many warts, but it is also true that it has the power of objects and object-oriented programming and API evolution over the course of many years, but it also has built in the power of C. And so it's like eminently practical in getting stuff done, but it also allows you to build large-scale APIs that you can evolve and migrate over the course of years, right? And I think that Apple's one of the unsung advantages that Apple has in its ecosystem is that it never had to have a COM or a Corba or other abstraction because of the way Objective-C worked, right? And so for me, this pushback from management became twofold, right? One is it forced me to think strategically about the problem instead of just technically about it. And kind of, they push very naturally on, okay, well, if Objective-C has problems, why don't we make Objective-C better? And I rose to the challenge and said, yes, let's make Objective-C better. Let's improve the memory management so it's more automatic and less bug prone. Let's add new features so it's more syntactically nice to work with and things like this. But there's an inherent problem with safety. And so you can't take the pointers out of C with it still being C, because pointers are the basis of arrays and like everything in C, right? And so the why do new language turned into well, if we want to improve app reliability and improve developer productivity and get improved security and these other principles that are universally valued, then you have to break from C and Objective-C. And if you're going to do that, well, heck, you might as well make a really nice language. And so once we got through that, there became a question of what is a really nice language? And the challenge there became, on the one hand, you have to have the API evolution and the large-scale app framework design advantages that Objective-C has, but you have to have the low-level bare metal performance that C has, right? And you need to be able to say, hey, I want to generate SIMD vector code or whatever it is, right? And so this is where Swift's design premise around, it is syntactic sugar around LLVM really came to the front, right? And so in Swift, for example, integers and floats and strings and arrays and all these things, they're all part of the standard library. They're not part of the language. And so int is just a struct in the standard library. And if int can be efficient, which it is, then that means that all user-defined abstractions are themselves efficient. And this drove a lot of very interesting points in the language space that people hadn't really pushed on before. And so it took off over time. We eventually grew the team, eventually released it to the world. And I was very happy to see that people seemed happy about it. And the big challenge there was that it was, let's say, still quite early, and it took a couple of years to work itself out. But it seems to have stabilized really well. And we've worked very closely with the community on the evolution of that and through open source.
Okay, I think that's great, and I think we touched on some of the lessons you learned there. So the great thing about talking to you is that we get to move on to another project. Of course, I suppose the next project I'd mentioned is one we've already talked about in some sense, which is MLIR. But you moved to Google, and you ended up working on MLIR. So you already talked a little about what it is, but can you say a little bit about how that ended up happening? What was motivating the work on MLIR at that point in Google, and how did it end up being used?
Yeah, okay. Well, so let me tackle the why did we need MLIR in the first place, and then I'll talk about what it is. Okay, so I'll start from problem statement. Mm-hmm. So problem statement comes back to one of the earlier questions, which is what's wrong with LLVM? Okay, so LLVM is interested in tackling the C with vectors part of the design space. But there are a lot of other interesting parts of the design space that LLVM, maybe it's helpful in some small ways, but it doesn't really help the inherent problem. So if you talk about distributing computation to a cluster, well, LLVM doesn't do any of that. If you talk about machine learning, and I have implicitly parallel workloads that are represented as tensors, LLVM doesn't help with that. If you look at other spaces, for example, hardware design, we're talking about this morning, LLVM has some infra that you can use in some ways to do some things there, but it's not great at that, right? And so what had happened, my journey over the course of many years is that many people were taking LLVM because it's a good thing and trying to get it to do something that wasn't designed to do, and having a lot of unhappiness and pain and suffering and leading into a dark place, right? So the other context was that within the Google and the TensorFlow team, TensorFlow itself, it's not widely seen as this, but it's really a set of compiler technology. And so it has TensorFlow graphs. It has this XLA compiler framework with an HLO graph. It has code generation for CPUs and GPUs. It has many other technology components like TensorFlow Lite, which is a completely separate machine learning framework with converters back and forth. And so what had happened is that TensorFlow had this massive amount of infrastructure and ecosystem where there's 7 or 8 different IRs floating around, and nobody had built them like a compiler IR, right? People think of TensorFlow graphs as a protocol buffer, not as an IR representation. right? And the consequence of this is that the quality around that was not very great. It was very research quality. Nothing was really integrated. There was all these different technology islands between the different systems. People weren't able to talk with each other because they didn't understand that they were all working on the same problems in different parts of the space. And so MLIR came from this idea of saying, how do we integrate these completely different worlds where you're working on a massive multi-thousand node machine learning accelerator like TPUs versus I'm working on an ARM TensorFlow Lite mobile deployment scenario, right? There's no commonality between those, right? And to me, what I realize is that there's a hard part of building compilers which has nothing to do with the domain. And so if you look at a compiler, you look at something like LLVM, a big part of LLVM is you have all this infrastructure for testing, for debug info, for walking the graph, for building a control flow graph, for defining call graphs, for like doing analyses, pass managers. All of this kind of stuff is common or can be common regardless of whether you're building a CPU JIT compiler or whether you're building a TensorFlow graph style representation where you're trying to represent matmul's and convolutions, because it doesn't, the representation on the compiler infrastructure challenge is invariant to the domain you're targeting. And so what MLIR evolved into, and this is working with a bunch of really smart people, by the way, not just myself, was taking this notion of a compiler infrastructure and taking the domain out of it. And so MLIR is a domain-independent compiler infrastructure that then allows you to build domain-specific verticals on top of it. And so it provides, in the box, the ability to define your IR, your representation, like what are your add, subtract, multiply, divide, load stores? What are your, what are the core abstractions you have? So for example, in software, you have functions. In hardware, you have Verilog modules, right? And so MLIR can do both of those, right? And by building that, it then provides all this useful functionality out of the box, which then allowed us at Google to say, okay, well, we have 7 different compilers. Let's start unifying them at the bottom and pull them onto the same technology stack so we could start sharing code and breaking down these barriers. Also, because you have one thing and it's being used by lots of people, you can invest in making it really, really good. And investing in infrastructure like that is something you often don't get a chance to do. And so MLIR, I'm very excited to see it's being adopted across the industry and many machine learning kind of applications and things like this. But I'm also excited to see it being adopted by folks on quantum computing. And, at Sci-Fi, we use it for hardware design and doing chip design kinds of problems. And any place you benefit from having the compilery, I need to be able to represent a design. I have a declarative specification of a thing, and I want to do analysis so I can find bugs or do optimizations or do whatever, and transform and lower into other representations. MLIR becomes very useful.
Okay, I think that's obviously really interesting and it's
and also
very helpful for the rest of the community. Yeah, and also Fortran. So, and we have
let me use Fortran as a concrete example. I should have mapped to the community, right? So Fortran, people have built compilers using LLVM for Fortran. But one of the problems that you have in Fortran, one of the many, many, many challenges you have in Fortran is you have Fortran 90 parallel arrays, you have OpenMP, you have many different options of how do you lower those high-level constructs down to a loop that the CPU executes with vectors, for example, or that gets distributed across the machine. And so one of the cool things that the F18 project is doing is they're representing these constructs in a way that you can use data flow analysis and all these compilery things to be able to lower in an efficient way down to something like LLVM. And so in that case, MLIR can compose and handle the high-level abstraction problems and let LLVM do code generation, which is what it's really good at.
Okay, and so we have about 5 minutes left in our time. So let me just sort of ask you some broad questions at the end, and say, from your standpoint as a as a technologist of sorts, what do you see as the top technology trends? What's sort of driving your work and your focus and your interests now?
Yeah, so there's a lot of stuff going on. I mean, there's a rise of accelerators. And one of the things I see, so I have worked for a long time in this boundary between hardware and software, and kind of flitting into the hardware space and hardware design, coming back up and trying to make software that actually uses it. And there's these really difficult unsolved problems with hardware developers now know many architectural microarchitectural tricks to make specific workloads go fast, but that's not useful unless you have software that can utilize it. And so there's a pretty big gap there that's growing between what the architects know how to do and how you can get widespread adoption of these technologies. One of the things that excites me the most about AI infra, for example, is that many of us in the industry worked on parallelization techniques and things like this. And so it's like 20 years of Silk and TBB and like all the cool things that we were all working on forever. And then the machine learning data scientist nerds come up with this idea of a tensor graph. And now, through the introduction of a tensor graph, you now have somebody working in a Jupyter notebook talking to a 2,000 node cluster and in Python. It's like, wait a second, what just happened? Right? And what happened was this innovation in representation, allowing one to capture the implicitly parallel representation that is true in a data flow graph and in a machine learning world, and then allowing the compiler stack to unlock that is, I think, quite profound. Now, the ML space is really important and exciting in lots of ways, but it's only one small part of the ecosystem. And so to me, I think it's exciting to see that kind of a breakthrough. Again, like data flow graphs have been invented before, like people have been doing neural networks for decades, right? But that kind of the realization in the commercial market, I think, is exciting. And I think that one of the challenges we have today is that it's kind of locked up in these overly specific framework implementations of TensorFlow for TPUs, right, which are looking at dense matrix multiplications but aren't very broadly applicable beyond that. And so I think there's a great opportunity to take this technology, take it out of the individual niches in which it's currently inhabiting and treat it as proven science. And now it's suddenly an engineering problem to make it more generally applicable, more widely available, pull more hardware into the space. And my hope and dream is that as we do this, then we get it so we have much more programmability, much more ability to take advantage of heterogeneous hardware, which is still a very big challenge. And as you do that, then you're unlocking the power of silicon, which is implicitly parallel. And this is just such an exciting time because in the decades of Moore's Law, for example, there was very little incentive to do the hard things when you could just wait 18 months and get something that's 2 times faster. But now that things are starting to change, like the economics and the power consumption, many of the other things that are changing in the space are forcing a bunch of innovation. And I love it. It's great.
Okay, great. And I think that's obviously very interesting. And we're going to have to wrap it up. Unfortunately, we've really reached the end of our time. Chris, are there any parting words of wisdom that you would like to leave the audience with as they pursue their careers and their interests?
No, I'm just happy to be invited, and I'm excited about what's going on in this community.
Okay, well, great. Thank you very much. And again, thank you to the organizers for inviting us and setting up our fireside chat. Sounds fire.
Yep. Thank you all.